So, hi everyone, my name is Martin, and today I'm going to be talking about our recent FOCS paper, Faster Δ+1 Edge Coloring, Breaking the M-Root-N Time Barrier. This paper is joint work with Sayan Bhattacharya from the University of Warwick, as well as Dean Carmon, Shay Solomon, and Tianyi Zhang from Tel Aviv University. Okay, so to start off, what actually is the edge coloring problem? So in this setting, we're given some simple undirected graph, G equals VE, and our objective is to compute an edge coloring of this graph, right? This is a mapping from the edges to some collection of colors such that no two edges that share an endpoint receive the same color. So in this picture, you can see that we have some simple undirected graph and that all of the edges that share some common vertex are colored differently, right? So we can assume that this collection of colors is just integers from 1 up to n. It doesn't really matter like what the colors really are. All that matters is which ones are the same and which ones are distinct. And we can also see that the number of colors that's required is at least delta, where delta is the maximum degree of the graph. And this is just because if you take some node of maximum degree, all of the edges that are incident upon it share this common node, so they all have to have different colors. So really, the interesting question here is like, how small can we make lambda, like the number of colors, right? Because trivially, we could just assign every edge in the graph a distinct color, and we could trivially compute an edge coloring of the graph. So the interesting setting is when lambda is as small as possible, basically. And a famous theorem by Weising from the 60s shows that it's always possible to compute a Δ+1 edge coloring of a graph. So we have this like very tight upper and lower bound of delta and Δ+1. And in general, it's actually NP hard to determine whether or not a graph admits a delta edge coloring. So Δ+1 is really the best that we can hope for from an algorithmic perspective. So another natural question that arises in an algorithmic setting is like, how fast can we actually compute a Δ+1 edge coloring of a graph, right? So Weising's original proof is actually algorithmic and immediately implies the existence of an MN time algorithm. And this algorithm basically works by scanning through the edges of a graph in an arbitrary order, and then for each edge, extending the coloring to this edge by flipping most of the colors of another edges, right? So this entire algorithm runs in MN time. And this was subsequently improved upon by Arjomandi and Gabo et al. Independently in the 80s. And they showed how to compute a Δ+1 edge coloring of a graph in M-Root-N time, up to some small polylog factors. And then some time after, Cinnamon was actually able to shave off this like extra root log n factor and obtained a clean bound of M-Root-N. So it seems challenging to kind of break through this M-Root-N barrier. And this also coincides with other like classical barriers for fundamental problems. The most obvious of which being general like exact maximum matching, which is obviously related to this problem since edge coloring is basically just partitioning a graph into matchings, right? So if we allow ourselves to use more than Δ+1 colors, then unsurprisingly, there are faster algorithms than this. So, for example, a recent result by Elkin Kuzmin shows how to compute a 1 plus epsilon delta coloring of a graph in m over epsilon time. So if epsilon is some small constant, then this runs in near linear time already. And very recently, Asadi showed how to compute 1 plus epsilon delta coloring in m log 1 over epsilon time, so exponentially improving the dependence on epsilon here. So this algorithm also implies that you can delta plus big O log n color a graph in near linear time. So really, if we have any like extra number of colors, the problem does become substantially easier. So there are many other papers on static edge coloring as well. And yeah, this problem has been explored extensively in the kind of like approximation algorithm context, right? So what if we really do want Δ+1 edge coloring of a graph though, and we don't want to use any extra colors apart from this extra one that we kind of need? So we were able to actually improve the running time of Δ+1 edge coloring using some new techniques. And in fact, we were able to show how to compute Δ+1 edge coloring in mn to the 1/3 time using randomization. So this algorithm succeeds with high probability. So this is the first polynomial improvement over this M-Ru10 bound from Gabo et al. So we continued working on this problem after we obtained this bound. And there have actually been some follow-up works after we released this. So independently and concurrently, Asadi tackled this problem using very different techniques, which are kind of in some sense the opposite of what we did, and was able to show how to compute a delta+1 coloring in n squared log n time. And this actually follows from the previous result that I showed on the other slide. And building on top of both this FOCS paper and this result by Asadi, and designing some brand new multi-step Weising chains, we were able to actually come up with an algorithm that runs in mn to the 1/4 time and improving over this result. And then we continued working on this problem and actually taking a very different approach which doesn't build on any of these papers or techniques. We were able to finally get this down to near linear time, and we obtain an m log n time algorithm that succeeds with high probability in constructing a delta+1 edge coloring of a graph. And this final result here is actually quite simple. I think it's much simpler than these other papers. And it's also combinatorial. The whole algorithm is basically just like flipping some carefully chosen alternating paths and constructing some other like basic combinatorial objects. Okay, so for the rest of the talk, I'm going to sketch over the proof of this mn to the 1/3 time algorithm. And at various places, I'll make some kind of like simplifying assumptions in order to kind of make some technicality simpler. So in particular, I'll assume that the graph is near regular and bipartite for simplicity. Although with a bit of like extra technical details, you're able to overcome these assumptions. Okay, so our algorithm basically consists of two key ingredients. So the first ingredient is what I'll refer to as the key lemma, which is really the main technical contribution of this paper. So suppose that we have some partial delta+1 edge coloring of a graph, chi, and let U be some subset of nodes such that we have lambda uncolored edges that are touching, like have endpoints within this set of nodes U. Okay, so it's basically like you should imagine U as being like a small vertex cover of these lambda uncolored edges. So we show in this key lemma that we can always extend this coloring chi to one of these uncolored edges in this much time. So delta m times the size of U over lambda squared time. Okay, so this bound might seem a little strange. I'm going to elaborate on this in a moment. So a very similar previous lemma by Cinnamon basically gave the following bound. So suppose we just have lambda uncolored edges, then we can extend the coloring to one of these edges in delta m over lambda time. And this actually implies a delta m time algorithm by just basically taking all of the edges in the graph, just having them all uncolored, and then just repeatedly extending the coloring to one edge. And this just gives this delta m times a harmonic series, right? So in this bound by Cinnamon, there is no vertex cover U, right? This is something that we introduced in ours. So really, the idea here is that our key lemma is kind of like a generalization of Cinnamon's lemma in some sense. And as long as this like value, size of U over lambda, is sufficiently small, we can actually get a polynomial improvement in the running time of this lemma over Cinnamon. And this is kind of how we get the polynomial improvement in our algorithm. So to begin with, I'm going to explain a little bit of the intuition behind Cinnamon's lemma and why it's true, and then kind of explain how this extends to our key lemma. So the intuition here is like, suppose you have lambda uncolored edges, then this like algorithm that achieves this bound, the way it works is that it kind of assigns some unique alternating path to every single uncolored edge, such that extending the coloring to this edge flips this alternating path, right? And every single uncolored edge has its own unique alternating path that isn't being given to any other uncolored edge, right? And it's known, it's a simple combinatorial effect, that the total length of all alternating paths in the graph is delta m. So the idea here is that we have lambda alternating paths that correspond kind of in bijection to these lambda uncolored edges that we want to extend the coloring to. And we have that the total length of all alternating paths, including these lambda alternating paths, is delta m. So then if we just sample one of these uncolored edges uniformly at random and extend the coloring to this edge by flipping this alternating path, then the expected length of this alternating path should be at most delta m over lambda, right? And unsurprisingly, with some basic data structures, you can implement the algorithm so that the time that it takes to flip the alternating path is proportional to the length of the alternating path, which basically gives us this delta m over lambda bound on the running time, in expectation at least, right? So the idea here is that we, instead of just assigning one alternating path to an uncolored edge, every single uncolored edge will now receive one of lambda over the size of u many alternating paths instead. So now we have lambda times lambda over size of u many alternating paths in total corresponding to all of these uncolored edges. So the expected length of one of these is now just basically smaller by this size of by this extra factor, right? So the expected length is now going to be a little bit smaller as long as this value is smaller, right? And how do we actually kind of do this? The intuition is that by grouping together uncolored edges in this kind of small vertex cover U, we can kind of blow up the number of choices of alternating paths. So for example, you can have a look at this picture. So suppose we have three uncolored edges that are just forming a matching, right? A small number of uncolored edges that are just forming a matching. How do we actually construct the alternating paths that are flipped by the algorithm in order to extend the coloring to these uncolored edges? You basically take one color which is available at one endpoint and a color which is available at the other endpoint, and then you consider the alternating path that it consists of both of these two colors starting at one of these ends. And then basically just by flipping these colors, we can then extend the coloring to this uncolored edge. But the problem is that there might only be kind of one or two free colors at each of these endpoints, so we don't have many choices for this path. We only have in the worst case a constant number of choices for the path. So we can't really do better than this bound of cinnamon if the uncolored edges are kind of spread out all over the place. On the other hand, if we now take all of these lambda uncolored edges and we kind of compress them together so that they share one single endpoint, this one endpoint which they all share now has many, many uncolored edges incident on it, right? So in this case where the size of u is equal to 1, it'll have at least lambda uncolored edges incident on it, right? So that means that it has at least lambda free colors. So now, instead of just only having one alternating path kind of starting from these external kind of endpoints in this star, we can actually consider lambda, one for every single one of the colors that are missing at this a central node. And this gives us lambda squared many paths instead of lambda, in this case where the size of u is equal to 1. And then this can be generalized to having larger u, and this is how we kind of obtain this speed up. So I am kind of ignoring various technicalities here. For example, what happens if these alternating paths end at the other endpoint of this uncolored edge? It turns out that this can only happen if the graph is not bipartite. So if you are comfortable with assuming that the graph is bipartite for the purpose of this talk, then this kind of actually almost is the entire proof. But even if the graph is not bipartite, with some technical details, we are able to kind of overcome the barriers and still make this argument go through. Okay, so the second ingredient we refer to as coloring with slack. So suppose that instead of computing a delta coloring, we want to compute a delta plus d coloring, where d is some parameter. So we can use this result which I mentioned earlier by Elk and Kuzman. So just kind of reframing it in terms, instead of being 1 plus epsilon delta coloring, it's now just delta plus d coloring. But basically you can compute a delta plus d coloring in delta m over d time, right? And here we refer to this value d as being the slack. And the idea is that the bigger this value d, the bigger the slack, the faster that we can kind of perform this operation of computing a delta plus d coloring. Okay, so our algorithm just takes these two ingredients and kind of combines them. So specifically, the way that our algorithm works is we sample some set U, some subset of nodes, by basically sampling each node independently with probability 1 over n to the 1 over 3. So then with very high probability, the size of this set U is just going to be n to the 2 over 3, okay? And then what we do is we take this subgraph induced on the nodes v minus u, after kind of removing these nodes in U, and we use this Alkan-Kuzmin algorithm to compute a coloring chi on this graph where the slack parameter is set to this value lambda over n to the 1 over 3, right? So we take our graph, we partition it into this set U and the set v minus u, and then this gives us three types of edges, right? Edges that are contained in U, like with both endpoints in U, edges that are fully contained in v minus u, and edges that kind of cross this cut. And we use this Alkan-Kuzmin algorithm to color all of the edges in v minus u. So the idea here is that removing kind of these nodes in U and all of their edges incident on them basically reduces the degree of the graph induced on v minus u. In fact, it reduces it enough that kind of like you basically expect all of the degrees of the nodes in v minus u to kind of fall by like a d, essentially, right? And thus, with high probability, the maximum degree of this graph induced on the edges in the nodes in v minus u is going to be at most delta minus d. So then when we kind of compute a delta plus d coloring of this graph, it will use up most delta colors. And thus, this coloring chi is actually delta plus 1 edge coloring of this graph. And now this is kind of like the starting point, and now the objective is to extend it to the rest of the edges in the graph, the ones that are incident on this set U. And also just by kind of like the running time of this Alkan-Kuzmin algorithm, this can be done in mn to the 1 over 3 time. Okay, so now suppose we've done this. We've obtained our edge coloring on the edges in v minus u. And now we have the lambda uncolored edges that are incident on u, which we want to extend the discoloring to. So this is kind of where we use our key lemma to just repeatedly kind of like extend the coloring to one more edge over and over again, incident on u. So while the number of uncolored edges is sufficiently large, greater than or equal to this value L, which we define, we just repeatedly apply the key lemma over and over again to just keep on extending the coloring to one more edge. And then once this value lambda becomes sufficiently small, basically once this bound becomes bad, right? Because this is good when lambda is sufficiently large, but then once lambda is too small, clearly this bound is going to be kind of like much worse than what you can do trivially. So at that point, we just switch to using just the standard Ising chain argument that he originally proved in the 60s when he first came up with his theorem, to just extend the coloring in n time to these edges. And then you can show by a straightforward calculation, at least assuming if you're assuming the graph is near regular, that the total running time of this whole process is just mn to the 1 over 3 time as well. And thus the total running time of our algorithm is going to be mn to the 1 over 3, right? So all of these parameters, their exact values aren't kind of too much. They're just kind of chosen so that we balance everything else, and the total running time of the entire thing ends up being mn to the 1 over 3. Okay, so thanks a lot for watching. I will be attending FOCS in person. So yeah, I'm looking forward to seeing all of you in Chicago. Thanks a lot.